Okay, so now let's look at the different types of deep learning. So there's not just one type of deep learning algorithm. Different architectures are designed for different types of problems. So let's look at the most popular one. So convolutional neural network, or CNNs, these are essentially for image processing and object detection. And then we have recurrent neural networks, RNNs. These are essentially for sequential data, like time series or text. And large language model fall under this category. And then we have long short-term memory networks, LSTMs. These are specialized RNNs for remembering long-term dependencies. We also have less famous ones like GANs, for example, generative adversarial networks. These are used for generating new data that resembles the training data. There's a radial basis function network. This is for classification, regression, and time series prediction. We also have multi-layer perceptrons, MLPs. These are the foundational deep learning architectures and is used for different tasks. You have self-organizing maps, which are for data visualization and dimensionality reductions. Deep belief networks. These also are used in image recognition, video recognition, motion capture. We have restricted Boltzmann machines. These are used for dimensionality reductions and feature learnings. And autoencoders. These are for unsupervised learning and dimensionality reductions. We use them essentially to get embedding vectors. Let's look now in details on convolutional neural networks. So CNNs, also known as convnets, are specifically designed for image processing and object detection. They're revolutionary because they can extract spatial features from images automatically. So CNNs consist of multiple layers and are specifically engineered to process images efficiently. So here's how the layers work. First, we start with a convolution layer. This is where CNN gets its name from. So the convolution layer applies multiple filters to the input image. Think of each filter as a small window that slides across the image, looking for specific patterns, like edges, corners, textures, or more complex features. When a filter detects a pattern it's trained to recognize, it will activate. The output of this layer is a feature map, showing where these patterns occur in the image. Next we have rectified linear unit. And so after convolution, the network applies a ReLU layer. And essentially what it does, it has an activation function that performs operations on elements. Specifically, it converts negative values to 0 and keeps positive values. The output is a rectified feature map. This introduces nonlinearity, which allows the network to learn more complex patterns than linear transformations alone would allow. We also have pooling layers. The rectified feature map will feed into pooling layer. And pooling is a downsampling operation that reduces the dimensions of the feature map. Typically, max pooling takes the maximum value from a small region, discarding other values. This will serve two purposes. First, it reduces the computational load because we can start with very high dimension input vector and keep reducing that as we do successive pooling layers. And this will allow us to focus on the most important features in each image, making it more robust to small shifts in the image. Finally, we have a fully connected layer. So the flattened matrix from the pooling layers is then used as input to a fully connected layer, which will classify and identify the images. This is like a traditional neural network layer, where every neuron connects to every neuron in the next layer. This is where the actual classification takes place. So this slide here gives us a CNN, an example of a CNN, and how it will process an image. So let's go over it. So on the left, we have an image of a bird. The image is the raw input to the CNN. So each pixel, we have the pixel intensity. We create a vector of all these intensities, and that's the input to the convolution neural network. The image then goes through multiple convolution layers with different filters. Okay. And then each layer learns to detect different types of features in that image. Notice how the representations get more abstract as we go deeper. Early layers will detect low-level features like edges and textures, and then middle layers will detect more complex patterns like parts or objects. Now, finally, at the end, we have a fully connected layer, which is this one right here, that takes all the learned features that we got at the end from after applying pooling and makes a final classification, bird or dog. So this is interesting because the CNN learned what features are important for identifying birds entirely from training data. Again, like we said, no human identified, for example, look for feathers or look for a beak. Now the network discovered all this automatically. This is a real-world example that shows applying this classification to a room. So we have a bedroom photo, and then the convolution and pooling layers extract features, again progressively. And then you can see multiple layers of processing, each extracting increasingly advanced features. And finally, we have a fully connected layer, which is in blue right there. It has a max pool layer. So the max pool layer right before it is this one. This is a fully connected layer, and the fully connected layer will decide or will classify the room, will give you probabilities that this is a living room or a bedroom or a kitchen and so on. So this is how computer vision actually works in the real world. Whether we're talking about self-driving cars, trying to identify pedestrians in an image, or traffic lights, or medical imaging systems detecting tumors, or a retail system recognizing products. In all these cases, we use a convolution neural network that has this architecture, but obviously in each application we use different types, different number of layers, and also depends on how accurate the input image is. Is it high density pixels or is low density pixels and so on.